Good morning, class. We are looking at chapter 2, limits. Here's 2.4, limits, algebraic method. We cover limits of sequences, limits of functions at infinity, limits of functions at finite numbers, and now algebraic method. So what we have covered, let's recall limits of functions at finite numbers, finding limits by numerical and graphical methods. Definition, limit of f of x as x approaches a equals L, the same writing as here. Limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. If this limit is infinity, negative infinity, or DNE does not exist, we say the sequence diverges. And to find limits, simply plug in the value and observe. In all of these cases, we are interested in the limit of f of x as x approaches a, from the left, from the right, from the left, from the right. And in all cases, looks like that. And they all give us the same limit, namely L. So the limit exists because one-sided limits are identical. What's the difference? In this case, even f of a equals L, which makes it continuous at a. In this case, f of a, the solid point has a y-coordinate b, so it's not equal to the limit, makes it discontinuous at a. In this case, f of a is not known, is not given, is undefined. Nevertheless, the limit exists. As far as horizontal asymptotes, the definition is that if the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L, then the line y equals L represents the HA, short for horizontal asymptote. In the case of a vertical asymptote, if the limit of f of x as x approaches either a, or a from the left, or a from the right is either negative or positive infinity, then the line x equals a is the VA, vertical asymptote. And again, reminding you of the one-sided limit. A function has a limit at a if the limit of f of x as x approaches a from the left equals L, the limit of f of x as x approaches a from the right equals L, and therefore the limit of f of x as x approaches a does exist, and it's equal to L. 2.4 limits, algebraic limits, and here's limit laws. Let f of x and g of x be defined for all x over some open interval containing a. Assume that L and M are real numbers such that the limit of f of x as x approaches a is L, the limit of g of x as x approaches a is M, and let C be some constant, and then each of the following statements holds. In short, all of these statements look like the algebra of functions, but algebra of functions on limits. So for example, the sum law for limit says the limit of f of x plus g of x as x approaches a equals limit of f of x as x approaches a plus limit of g of x as x approaches a equals L plus n, meaning the limit of the sum is the sum of the limits. Difference law for limits. The limit of the difference is the difference of the limits, L minus M. Constant multiple. The limit of C times f of x as x approaches a. C is a constant, you can take it outside the limit. You get C times L. Product law. The limit of a product is the product of the limits, L times M. The quotient law, the limit of the quotient is the quotient of the limits L over M. Needless to say, as always, the denominator, in this case, M, cannot be zero. Power law for limits, the limit of f of x to the power of n as x approaches a. We take the limit of f of x as x approaches a first and then raise it to the power of n, or L to the power of n, for positive integer n. The root law says the limit of the nth root of f of x as x approaches a is the nth root of the limit of f of x as x approaches a, or the nth root of L. Of course, for all L, if n is odd. Remember, when the index is odd, there is no restriction. However, if the index is even, L must be greater than or equal to 0. Direct substitution property, a continuous function at a has the following limit values. The limit of f of x as x approaches a equals f of a. Let's, as a warm-up example, let's remind everybody of the limit laws. The limit of x squared minus 3x plus 7 as x approaches 4, you have a polynomial with 3 terms, make up 3 limits. Limit of x squared as x approaches 4 plus limit of minus 3x as x approaches 4 plus limit of 7 as x approaches 4. According to the limit laws, this is the limit of x as x approaches 4 the second power, and this negative 3 comes out. When we have limit of x as x approaches a, then you can replace it with a, in this case 4. So this is 4 squared minus 3 times 4. A constant is itself. 16 minus 12, 4 and 7 is 11. Or as we've been doing, just plug in. Plug in. 4 squared minus 3 times 4 plus 7 equals 11. Evaluate the following limits. If they exist, we are given a graph, and reminding everybody of the one-sided limit exists if both sides have the same limit. Part A, limit of f of x plus 5 g of x as x approaches negative 2. Using the limit laws, we make up 2 pieces. The limit of f of x as x approaches minus 2 plus 5 times limit of g of x as x approaches minus 2. So we look at each piece. So we are interested in the limit of f of x as x approaches minus 2 is the red function. And here's number negative 2. This is negative 1. This is negative 2. So from the left side and from the right side of number negative 2. Here's the left side. We are moving towards this point. Here's the right side. We are moving towards the same point, which has the y coordinate 1. So the limit of f of x as x approaches negative 2 is 1. What about g of x, the blue function? The limit of g of x as x approaches negative 2. So along the x-axis, and here's negative 2 from the left, from the right. We are moving towards the same point again. And the y coordinate of that point is negative 1. So the answer is 1 plus 5 times negative 1, which is negative 4. Part B, the limit of f of x times g of x as x approaches 1. Again, we use the limit laws to cut this into 2 pieces. The limit of f of x as x approaches 1 times the limit of g of x as x approaches 1. And we are going to look at each one individually, starting with the limit of f of x as x approaches 1. So here's number 1 on the x-axis. So from the left side, we are coming this way along the curve. From the right side, we're coming this way. And in both cases, we are moving towards this point, which has a y coordinate positive 2. What about g of x, the blue function? The limit of g of x as x approaches 1 does not exist. Why is that? Because one-sided limits are different. So 1 from the left puts us in this branch, and the y coordinate of this point, because we are moving towards this point, is -2. And from the right side of 1, we are in this branch moving towards this hole, which has a different y coordinate, namely -1. Since the two are not the same, the limit of g of x as x approaches 1 doesn't exist. Therefore, the limit of the product does not exist. The limit of sum or difference doesn't exist as long as one of them fails. I'm going to look at a second method for part B, meaning what if I right here try to find the limit as x approaches 1 from the left and then 1 from the right. As well, as far as 1 from the left, we look at each one from the left and then we multiply. We already know that the limit of f of x left and right makes no difference, is 2. G of x from the left is -2. So the product of 2 and -2, which makes it negative. And it's not equal if we look at the same, but from the right. The limit of f of x times g of x as x approaches 1 from the right. Again, it's this one times this one. This one is 2 no matter what, x approaching 1 from the left or right. But this one from the right is -1. The product of these two numbers is -2, and the two numbers are not the same. The limit does not exist. Also, I want to add something, because we see a solid point, we see a hole, and we want to distinguish between the two. I want to explain f of -2. So here's -2, and you're looking for a solid point. This is a solid point which has a y coordinate 2, okay? Which means, of course, it's different than the limit, okay? And that's why it makes it discontinuous at that point, the function f of x. Also, let's look at g of 1, the blue function. Here's 1. So you look for, when we want the functional value, not the limit, we look at the solid point, and this point has a y coordinate -2. So distinguish between functional value and limits. All right, the limit of absolute value of x over x as x approaches 0 does not exist. Let's find out why. First and foremost, the concept of a one-sided limit is being reminded. Recall that absolute value of x is x. If x is larger than or equal to 0, minus x is less than 0. Please understand the meaning of this is, if x is positive, let's say you are looking at absolute value of 2, you just drop it and you say 2. But if you're looking at absolute value of -2, you are here, which means you put the opposite of this number. This minus x means the opposite of -2, which is 2. So please don't be under the assumption that this means negative. This means the opposite, which makes it positive. And so with that being the case, if I want to evaluate this function, absolute value of x over x, I look at two cases where x is positive and x is negative, and we don't consider equality because the denominator contains x. So when x is larger than 0, not larger than or equal, just larger, we get x over x, which is 1, and if it's smaller, we get minus x over x, which is -1. It's a piecewise defined function, and the graph of the first one, y equals 1, is a horizontal line which starts from 0, not including 0, and goes to infinity. This one, y equals -1, is also a horizontal line that is true for x less than 0. So the right side doesn't exist. And the reason we have a hole here because we don't have the equality. And as you can see, the limit of this expression, absolute value of x over x, as x approaches 0 from the left, is taking us this way in this branch to -1, or just look at the answer. But from the right, obviously, is taking us to this point, which is +1, or just keep it from the definition. And the limit of absolute value of x over x as x approaches 0 does not exist because they are not identical. The limit only exists if both sides result in the same thing. We want to find the following. It means all we have to do just plug in and observe. So if we plug in here 2, we get 2 times 2 squared plus 1. We get 3 times 2 minus 2. Please understand 2 squared, 4 times 2, 8, and 1 is 9. 3 times 2, 6 minus 2 is 4. Square root of 9 over 4 is 3/2. In other words, plug in, it works out, you're done. If you plug in -4, the denominator becomes 0. The numerator becomes 1/4 plus 1 over -4 is 0. So you get 0 over 0. And because this is an indeterminate form, first let's write it. Let's remind everybody. This means we are dealing with an indeterminate form. An indeterminate form means more work, means algebraic technique must be used. And because this is a complex fraction, the technique is LCD, which is 4x. And then the reason you put 4x over 4x because this expression is 1. So you multiply by the top. This gives you x. This gives you 4. And these two, you write it as a product. But I want to make a point of when x is approaching -4, x plus 4 becomes 0. And you never want to distribute. You are hoping through the process you can get rid of x plus 4 because it is the 0 in the denominator that creates a problem. And we can do that. And now if we replace the x with -4, we get -1 over 16 as the final answer. Part C, the limit of x squared minus 25 over x squared minus 5x as x approaches 5. If you plug in, you get the same thing, 0 over 0, indeterminate form. You're dealing with a rational expression. The technique is factoring. And remember, x is approaching 5. We should have a factor of x minus 5. If it's approaching 10, we should have a factor of x minus 10. If it's approaching -8, we should have a factor of x plus 8. You factor the top, a squared minus b squared. Again, the top is class x squared minus 5 squared. So x plus 5x minus 5. The bottom, you take the x out. These two cancel each other. We get 10 over 5 and it simplifies to 2. Pretty straightforward. All right. So if you plug in, you get 0 over 0. You have a rational expression. And again, reminding you that when we get 0 over 0, it's indeterminate form, right, everybody? Indeterminate. Which means more work, which means use algebraic techniques, which means in this case, we have to do factoring. And remember, x is approaching 4. You should have a factor of x minus 4. We do. We get the limit of x times x minus 4 over x minus 4 times x plus 1. As x approaches 4, these two cancel each other. And if we plug in 4, we get 4 over 5. Over here, if we plug in again, we get 0 over 0. It's an indeterminate form. And because we have a square root, we use its conjugate, which means we're going to multiply by the same thing. We're going to change this to a plus sign, and we divide by. The reason we use square root of 1 plus h plus 1 over the same thing is because we can only multiply by 1. So this must be 1, and it is. Now, when you multiply these two, you get a minus b times a plus b, which is a squared, square root of 1 plus h squared, minus b squared. And so we get 1 plus h minus 1. As far as the denominator is concerned, because h is approaching 0, you're hoping to get rid of that. You never distribute. 1 and negative 1 cancel each other. H and h cancel each other. And now if we plug in, 1 and 0 is 1, square root of that is 1, 1 and 1 is 2, so the final answer is 1/2.
So, Professor, just for like further clarification, when you deal with those problems, when you have like an indeterminate, you always want to refactor completely and then plug in?
When you get to indeterminate form, in the case of a rational expression, you factor. In the case that you have a square root, you multiply by its conjugate. If you have a complex fraction, you multiply by LCD. So when you get to indeterminate form, you use your algebraic techniques. And with enough practice, we know which algebraic technique we use where.
Oh, okay, I see. Thank you so much.
My pleasure. We plug in negative 4 makes denominator 0. This is 16 when you square it. Negative 4 squared is 16 and 9. 25 comes out as 5 minus 5 is 0. So you get 0 over 0. Indeterminate form. Now, what would be the technique? We just looked at an example. When we have a square root, the technique is to multiply and divide by its conjugate. So this one minus 5, you make it plus 5. And then you write the same thing in the denominator because this expression must be 1. You can't multiply by just anything. So when we do that, we are looking at a minus b, a plus b. So you're looking at a minus b times a plus b, and the answer is a squared minus b squared, which means the numerator is the square root of x squared plus 9 squared minus 5 squared. So this is x squared plus 9. This is minus 25. And these two numbers add up to negative 16. And the denominator, you never ever touch it. You write them as a product because x is approaching negative 4. X plus 4 is a problem. Clearly, the numerator is x squared minus 4 squared, which is x minus 4x plus 4. We can drop the common factor of x plus 4. Now we apply the negative 4. So to the top, negative 4 minus 4. To the bottom, negative 4 squared becomes 16 under the radical. This is negative 8. 16 and 9 is 25. This comes out as 5. So this is negative 8 over 5 plus 5, 10 equals negative 4 over 5 as the final answer.